a bit late, but it's fine. So, hi everybody, and welcome to this week's seminar. Today we have Uwe Kirscher with us from Tubingen, the University of Tubingen. Uwe began his academic career in the University of Munich, and then kept on studying there for his master's and PhD. He then moved to Curtin University to pursue his postdoc, and finally returned to the University of Tübingen, where he took the position of a research associate. In research, Uwe is very much interested and invested in a wide range and an increasingly wide range of applications for the Paleomagnetic method, from the application of Magnetostratigraphy in lake sediments to study paleoclimate and to do climatic reconstructions, to understanding the tectonic histories of large origins in Central Asia, and recently reconstructing paleo altitudes really in deep time to track the supercontinent cycles. But I think today we're going to hear about something, entirely different, a fourth application that he's been using, and I'm very happy and excited to hear what you have to say. So take it away.
Yeah. So thank you very much for the introduction, and also for the possibility to give this talk in your seminar series. As I said before, I would have liked very much to actually come to Jerusalem and give this talk in person, but yeah, we unfortunately this is not possible. But I think it's good to do it now, and hopefully I can come and visit you later or early next year. Yeah. So as Uri said, by training, I'm really a geophysicist, and then I'm applying paleomagnetism in a wide range. And I really think that paleomagnetism has this ability to can be applied in a huge range of different times, and because of his nature. So today, also because Israel has one of the famous hominid sites, which is particularly important for migration of hominids. I will talk about magnetostratigraphy in human evolution, and I will start with a short introduction about two very special sites in hominin migration. So the migration of hominins out of Africa in like 2 to 1 million years ago. But then I will, after showing a bit of the background of this magnetostratigraphy technique, I will come to like the three last studies I have done, which is not in the Pleistocene, let's say, in the young evolution of hominids, but in the Miocene, which is plays a much bigger role in terms of Eurasia in this realm, but I will show this later. So first of all, I will start with a citation which I found regarding Homo naeldi, which was found very recently, and which was in South Africa, and which was thought by the time that they discovered it, they thought they found the missing link, the oldest kind of the genus Homo. And during the studying these remains, like I think after realizing the actual age of this, Bill Junger said that without a doubt these fossils are more curiosities than game changers. And this I thought was a very nice sentence, because it shows that if we don't know the actual age of a finding, this can mean many different things. Like the same finding at 3 million years old, or which they thought this might be, or 300,000, which it ended up, can mean very different things in terms of human evolution. So this then John Kappelmann, which is one of the few paleomagnetists actually working on this in this topic, he said that the majority of fossil primates and human archaeological sites are found in sedimentary rocks, which are very hard to date, because normally there's no like volcanic layer which can be absolutely dated. So paleomagnetism offers an alternative dating approach, and we will see this later, that what kind of dating method magnetostratigraphy in this kind of sections really means and what it really is. So as I said, I will start with the Pleistocene, like between 2.5 and 1 million years, the earliest out of Africa migration of hominins. So the bipedal hominins, what Homo sapiens and Homo habilis, Homo erectus belongs to, and then the case studies from the middle to late Miocene, which is more 12 to 5 million years ago, all in Eurasia. I will not talk about Africa because I haven't been really studying Africa that much. So first of all, this is like the known important Pleistocene, like from the early Pleistocene, the sites which play a big role, and of course there is there is Ubadia here in Israel, which is one of the very important ones, and also the Manisi, which is thought to be the oldest one with the best preserved like human remains. There is you see other numbers here in China, which 2.1, but these are only artifacts. And also, the age of the Java hominids, this changed a lot. So these are really in terms of human evolution studies, as far as I understand it, these are the two key sites which show which can be used to reconstruct the migration, how the migration out of Africa actually happened. And first I will, because I started to work in Georgia, I will start with Manisi, which is in Georgia. This is the Caucasus, like between the lower and the upper Caucasus, between the Black and the Caspian Sea, and is a very nice country, a very nice area. It has a lot of the big mountains. It's famous for its churches, like one of the first countries with Christianity as state religion, I think. It's famous for its geology, as you've seen in the starting slides, a very nice Miocene outcrops, and also, not much older stuff, I think. Don't remember. It's famous for its wine, maybe not as good as the Israeli wine, but a very nice dry red wine, and also for the chacha, which is made of grapes, is a liquor. And of course, it's very famous for its the Manisi site, which I think this is David Locke-Badnitze, who is the director of the museum, and is a very small site. Is more archaeological site, but then this old skulls. I think now there are 4 or 6 skulls have been discovered, and also the dating took some time. So this is Locke-Badnitze again, and is a nice example how magnetostratigraphy has been used to date this site, because there is a basalt underlying the skulls is found somewhere here in this sediment lying on top of the basalt, but the basalt is underlying it, so there's no information how old the sediment actually is. So this is the magnetostratigraphy. I will come to this later and explain a bit at least what these points and colors are. But the thing is that the Mashavera basalt is 1.8 million years ago, which is one of the youngest normal polarity subcrons within the Matuyama cron. So this is normal polarity. This is fine, like we have today. But then they have shown that the sites have been found just on top of it. So it's just a bit younger than the top Olduvai transition, which is about 1.8 something. So this led to the age estimate of the Manisi, which is about 1.8 or slightly younger, which is important because it's really the oldest hominin outside Africa at this age. And the other thing is, I at a conference in Georgia when I was working, I had the pleasure to meet Professor Bayusef, which is famous for Ubaidia, and which unfortunately died last year, I think, or some time ago, and which was a great experience because, I mean, one of the big archaeologists, and he was also working, I think, more in archaeology, a lot in Georgia, which has also a lot of younger archaeological findings. But in this one conference about Manisi, he was also there, and he gave a talk, and this was very interesting. And this brings me to the next famous site, which I haven't been there, so I will not talk that much about it. And this is the site in Ubaidia in Israel, and this is a picture of I think Bayusef's 93 publication. Is more, as I understand, is more famous for the tools, for the hominin tools, but also like some actual human remains have been discovered there. And the interesting thing about Ubaidia to me is also the story about the age, because this is a paper by Repenning in Nature in 82 actually. I was not born yet. And they claimed there is no based on the artifacts and mainly on the biostratigraphy, there's no reason to make it younger than 2 million years old. So they argue that it's possibly older than 2 million years. And then a response by Neil Opdyke, which is one of the big paleomagnetists, or was one of the biggest paleomagnetists. He said that this is not true, and it might even be as young as 1 million years. And he criticized the paleontological arguments what Repenning brought forward. They made a response, so this was not clear at the time. After that, I think in 2005 there was a PhD thesis from the University of Jerusalem, and I couldn't find it, so it's I think it's not available online, just for people from the university. And they agreed with Opdyke, which just wrote that there is reverse polarity, which might be like Matuyama, like between 1 and 2. This doesn't, just the reverse doesn't mean much, unfortunately. But this PhD thesis claimed that there's some small crons which may be related to some subcrons, and which is potentially has an age of between like 1.1 and 1.45 million years. And then some electron spin resonance dating, which is a great technique, but I think as far as I read it, it's at the beginning it was thought only to be working until 500 years ago, and now but now they're pushing the limits. So they had great results for Ubaidia, and they said it's between like 1.2, 1.3 million years, which makes a lot of sense and agrees with this magnetostratigraphy results. So this is now the state of the art. And then a nice study by Ron and Levy came out from the Erk El Amma formation, which is by geologic correlation older than Ubaidia. And there they had some nice results with everything a paleomagnetist wants, and they found the Olduvai subchron. And so this is 1.8, it should be older than Ubaidia. So I think everything makes sense now. And also a nice thing, what they did is they showed a precise plot of inclination, and they argued that one of these like precursors to the actual reversal, which is an interesting thing, is not well understood. And now I think they claim it's happening all the time when a reversal is happening. But this is, I once tried it, and to argue with the geometry of the field to define or to identify a specific chron. So this always makes sense now. And yeah, so it looks good, but also there you see the evolution of the dating of such a site, which is very common in these studies. So now I have some slides for the background, because not everyone, I think, is expert in this technique, especially magnetostratigraphy. So first, about the Earth. The nice thing about the Earth magnetic field is that it's like to first or like 90% of it can be seen as a dipole. So on every place there is a certain inclination, and the inclination is the angle under which the magnetic field lines cross the surface. And this is very important for the paleogeographic reconstructions, because whenever such field lines get captured in a rock, we can measure the inclination, and then we can propose that this inclination was the same as during deposition, and then we can reconstruct the paleolatitude, which is the basis for paleogeographic reconstruction based on paleomagnetism. And the other, or I mean, maybe the most important thing about our magnetic field is that it actually protects us from the solar radiation, which is a necessary thing for the atmosphere even. And so there's always this debate how old our magnetic field is, and if it was actually necessary for the evolution of complex life. And then on the other hand, if the Mars had a magnetic field, and if it had one, it also could have had an atmosphere, and also life could have evolved on Mars. So there's a lot of things related to the existence of a magnetic field. But we are sure now that if a planetary body does not have a magnetic field, it cannot have like any kind of life developing on it. So as I said, is the how we describe the magnetic field is a field. So it has a direction and an intensity, and the intensity is very important, but is very hard to reconstruct. As I mean, Ron knows this much better. So trying to reconstruct the paleointensity through Earth history is a very complicated thing. But the direction is captured fairly nicely. So if we have a geographic north and a magnetic north, this is the present day declination. So we have always a declination because the magnetic field is not stable, but it's around 0 or 360 degrees at the present day, and it wobbles around it, so it might change. And this angle of the field lines passing through the surface, this is called the inclination, and this is a map of inclination from 80 plus to 80 minus. So this is really relating to the projection. So not all the weird appearance of the field lines is actually related to the complexity of the magnetic field, but it has, of course, some additional. It's not an ideal dipole, but it looks different, which is good because it has been used in navigation of ships from the oldest records, I think, are from the British Marine. And then we're coming closer and closer to understand how the magnetic field is where it's generated and how it's generated. So we know that is produced in the liquid outer core, and is a lot of is highly enriched in iron, the outer core, and is the fluids. So the particles are moving, the charged particles are moving around. And this is creating the magnetic field in the end. So, and with mainly related to an effect called the geodynamo. So, it's a self-exciting process where particles getting moved to the rims, and then the current is generated, and by that the magnetic field lines are getting strengthened. Is still a question how it actually started. So, this self-exciting process it does not say anything about how it started, but it's there and is working. So yeah, there's a lot of open questions, of course. the good thing about this dynamo is that it works in both ways. So if the dipole is oriented to the north or to the south, actually doesn't matter for the fields, for the process. And this is very good because the fact that it's reversing every now and then is really the basis for using paleomagnetism for dating. And it's this is a fairly old thing that, like, already in 1906, Bernard Bruns found in southern France, like volcanics, where he measured them, and he found that they have, here you have a stereographic projection with, this is like normal polarity, what we said, like when the field lines get captured in the rock have the same orientation as they have today. But he found that there's also in these basalts, they also have, every now and then they have a reverse polarity. So the field lines are not pointing towards north and down, but up and 180 degrees or so to the back. So they're really antipodal to what they are today. And I think by the time it was, they didn't really understand the importance of their finding. But then more and more people added this, like Matuyama in 29 also found this, that also in a consistent way, there is parts of the rocks which can have a reverse polarity. So not a normal, which is the one today, but a reversed one. And like it took some time until people like Cox, they put together like this kind of stratigraphies for the last 1, 2, 3, 4 million years, and they found periods where we really see only normal polarity. This, of course, this evolution goes hand in hand with improved dating techniques always. But then they also found consistent periods which have a reverse polarity, and then also some smaller phases. And then they really started to argue that maybe there was some kind of a stratigraphic evolution of periods of normal and periods of reverse polarity. And at the end of this, there is this column in the geologic timescale, which is called the global polarity timescale. And here you see the black things are really periods of normal polarity, and there is also peculiar periods like the Cretaceous normal superchron, which are long periods of like tens of millions of years where the field is not changing. And this is creating huge problems for modelers, because this is very hard to model, these periods of stability, and periods like the Jurassic or also the Miocene with a lot of reversals of the magnetic field. This is good for us because it, as you see, I mean, this is really happening in a chaotic way. So there's no way this is where you can argue, okay, we can say when a reverse is really happening. So we expect one now, but when this is happening, this is really an open question. And the only thing what has been done is if you plot this is the reversals, and this is like the reversal frequency, the yellow thing, and then other proxies like this is related to the full plate reconstructions, where you can reconstruct the subduction rate and subduction frequency, how much is subducted, the length of subduction. And then people argue that there is certain cycles of a lot of reversals, and then there's periods of no reversals, and this is really related to subduction and to stuff happening at the core mantle boundary. But this is really like, yeah, I mean, nothing is sure, and there's a lot of things to be done, but this is like on a long time scale, like 500 million years, how the magnetic field is really the quickly changing magnetic field is related to things happening in the mantle on a whole different time scale. There's indications, but this is I think we're a long way to go to understand what is really happening there. And So what are we doing actually is we're drilling this small cores with like drills like this is like a chainsaw engine and a drill, and this is water coming. And then we have to orient it because we are interested in the direction of the magnetization of these samples here. So we just take the compass, sun compass, every now and then, if the local declination is very high, and then we measure. This is at the time we didn't have a shielded room. Now we have a shielded room, which is really creating a zero field environment to get a very high precision, because these samples, for example, like a sediment, Cenozoic sediment from Central Asia, is really not very magnetic. So we need very, very precise instruments, and this is like what you also have in Israel. They look a bit different every now and then, but this is like a cryogenic magnetometer, this here, and this is an AF coil to demagnetize it. And yeah, and then to identify the certain components, we stepwise demagnetize it, either with alternating field or with just heat, so just an oven. And then we can identify the polarity and the different components, if there is a like a viscous component on top of it. But then if we are happy with this, we have the result is if you have a normal or reverse polarity in terms of magnetostratigraphy. And then the thing actually is that magnetostratigraphy is never, because it's not an absolute dating method, it can never be applied in a singular way. So it always has to be combined with other things. And so the main thing, or the starting point, normally is in sedimentary environments, especially in human evolution studies, is biostratigraphy, where the animals give kind of an indication how old this is, which is always a bit problematic, because there is problems like endemism, where certain animals can survive much longer in a like a refugial area or something. So this can lead to big problems. So this is then combined with magnetostratigraphy and like sometimes even chemostratigraphy, and then cyclostratigraphy to refine the age further. And this is all fine, but this can, if this is internally consistent, it can still be very wrong. So absolute dating is always is always required, I would say, in some way. I mean, normally in these sites it's not possible, but then you can go somewhere else and then like relate your things with other sections, and then get a absolute age in the end. So yeah, this is the big thing of magnetostratigraphy. Is not a dating tool, is more a correlation tool. So if we have a result like this, we sample the section, we have an interval of normal polarity and then 2 intervals of reverse polarity. We actually don't know where we are. And this is, you have seen before also here the situation in the Pleistocene, like the out of Africa story. You don't have a lot of reversals. So the pattern is fairly straightforward. And if you know you're somewhere here or somewhere here, if you get just one reversal, you could be fine with an absolute age. But in the Miocene, if you get older, there's first thing, there's a lot of reversals, so the pattern is quite complicated, and then you really don't know where you are. So the approach has to be a multidisciplinary approach. And so magnetostratigraphy can play always a crucial role, but only in getting the last step of age estimation. Yeah, so this is what I said before. This is the first order chronologies based on biostratigraphy, and then with the barcode, the magnetostratigraphy, and then within the chron, cyclostratigraphy so the relation of orbital cycles to certain parameters in the sediment. This can then yield a even preciser age estimate and that change in sediment accumulation rate within the section. And then I mean, maybe this should have come earlier, but the principle of paleomagnetism is that the magnetic field can be recorded in a rock. And we know fairly well that a thermoremanent magnetization, so a lava which is cooling. So if the lava is still hot, it's above the Curie temperature of the most important magnetic minerals. So that means that these minerals can move freely, whatever they want. And when it's cooling down, and they get aligned with the magnetic field lines here in blue, but when it's cooling below the Curie temperature, these particles get fixed, and this will record the magnetic field lines. So when the magnetic field lines then change, these particles will have their original orientation, and they don't move anymore. And then it has been shown that this is also happening in the sediment. The process is a bit more complicated, but the magnetic, like the small dipoles, small particles, small magnetite particles, for example, falling down the sediment column, they get oriented more or less along the field lines. And when the sediment gets solidified, then they actually stay in this orientation and yeah, record also the magnetic field. And then we can go through the sediment column or through a volcanic sequence and actually reconstruct the paleo orientation of the magnetic field. All right, so this to the introduction, and now we come more to the Miocene, which David Bagon called the golden age of hominids or hominoids. I will mostly call them hominids. To me, this is from the genus Hominidae. So this is including gorillas, chimpanzees, and Homo. And yeah, I'm not so much into, as I said, I'm not a paleoanthropologist, a paleontologist even. So to me, this is a fascinating story, the hominid evolution. But I want to be clear that I'm not discovering skulls, and I'm not like the end of the story, like putting a finding into the evolutionary concept. This is, other people have to do this. But as this Bill Junger said, the age is crucial, really. So I think this is a nice example of a topic where different disciplines have to come together to make the story actually consistent. So this is a map of here's Africa and here's Europe. It's a bit of a strange projection, but yeah, this is what David used. And here you see the middle to late Miocene hominids from Europe. And the important things is here's Udabno in Georgia, and here's some European, some from Greek, Turkey, where a lot of findings, also Italy. And I will talk about 3 examples. One new one from Hammerschmiede from southern Germany, then some footprints from Crete, from Trachylos, and then again from Udabno, because also there the age evolution is not straightforward. And the interesting thing, really, so this is a plot of, don't look too much into the details. I've done this a couple of years ago. I obtained the hominid findings from a database, and this is taking the age, so the middle age, if there is an age range, and just plotting them versus their latitude. I mean, paleolatitude strictly, but this is so young, so the present day latitude also does the job. And then just a running average through this. And the interesting thing is, of course, now once they became Homo sapiens or modern hominids, they spread just everywhere. And you have this time where they just appear in Africa. So really the Pliocene, everything is happening in Africa. And we are sure that they emerged also in Africa in the early Miocene. But the interesting thing about the Miocene is that it seems here that the appearance of hominids in Eurasia is correlated with not much happening in Africa. And this doesn't mean that nothing happened in Africa. It could also mean that we just don't find hominids from Africa. However, it could also mean that there was some migration into Europe early on in the early Miocene, and then the migration back to Africa and then back to Europe. This is highly controversial, of course, and I don't want to like comment on this, but to me this is just an interesting thing. So this means why did they go there, and why did they disappear again from Europe? And this is a interesting story, and this is the last piece of information is really from the Trachylos footprints, which might indicate that a lot more happened actually in Europe that we believed. But yeah, as I said, the age is very important to make this kind of when they appear and if they migrated from here to there. For this kind of arguments, the age constraints is very important. So this is just a map of the middle late Miocene hominids in Western Europe, Central Europe, Balkans, Anatolia, and Caucasus. And I mean, don't worry too much about the details, but this is a newly found hominid from southern Germany, which the sediment is between 11 and 12 million years. The next one is Udabno, which the last age estimate of my Spanish colleagues is about 7.5, which they claimed is really the last member of the Dryopithecines. So it could just survive so long because it lived in the refugial area of the Caucasus. And then really the Trachylos footprints, which are newly found footprints in 2017. I think there's still some problems with the footprints. I mean, obviously there's footprints, if they're not like Laetoli, they're sometimes not as, there's a lot of problems with them. And there's still, I think, is not clarified if they're really upright walking hominids or not. But to me, my main problem with this was the age constraint was really very loose and had also some mistakes in it. So they said it's older than the Messinian salinity crisis, so somewhere here, a bit older probably. But the old age constraint was really not defined. So it could be as old as 8 million years, which would made it even more problematic. But so to really argue with these footprints or to really put them in perspective, a precise age is really needed for them. So the first one is from the paleontology professor here in Tübingen, from Madeleine Böhme, and she termed it Udo, and is an important finding because it's fairly complete for the time. So a lot of postcranial material and also some teeth, of course. And this number here, so 11.6, this is what I contributed to this whole story. And it's such an important finding because it's claimed to be like the last common ancestor between chimpanzees and humans. And it had some especially the knee bone and it has some. It looks a bit like a upright walking primate, but it was certainly not hominin like upright walking. So not like bipedal, but it like my professor, she claims that this is a new type of walking, and this is really the way the last common ancestor moved around. And from this, the chimpanzees and also the bipedal hominids evolved, and at around 12 million years. So this gives new information on this chimpanzee human split in human evolution. And this is the site here. This is Hammerschmiede in Bavaria, and this is like a cross section. And here's Hammerschmiede, and because it's just 20 meters and we couldn't really make any sense of it, we decided to make a drill core here close by, which is this one here, and which includes the clay pit, and which captures a lot more stratigraphy. And these are the paleomagnetic results. So this is the site, we have a normal polarity and then a small reverse polarity. And this is the drill core, which looks fairly nice. We have some agreement between the two. So this normal polarity here seems to fit. Of course, we cannot use the declination here because it's a drill core. So, but we were happy with the correlation. And then we had some trouble in correlating with the polarity timescale, because in the time which was indicated by the biostratigraphy. So mainly there was not the real horse, and so it's older than 11.2 when this Hyperion disappears. And then based on the correlation with sites in Austria, this is Gradkorn, it should be between 11 and 12 million years. So this left us this window of mostly reverse polarity. So we had to infer two phases of huge, two large hiatuses to make this fit. But yeah, in the end, we ended up with an age of around 11.6, what you had before. So within this small normicron. The second story is Udabno. Is here some more pictures. So here's the large Caucasus. Here's there's the small Caucasus. This I think the Manisi is somewhere here. And yeah, this is the nice section of Udabno. And these are the tooth of Udabnopithecus, which have been found some time ago. And this is a paper by Agusti et al. From Barcelona, and this is what they came up with. So just normal polarity and some small one. This is a section of like 300 meters, and they put it based on a biostratigraphic correlation with a site in Greece. They put it about 7.6 million years ago. And we went there again and did some more measurements, especially because there is also absolute ages, and this is still in progress. So we made a new section, which is this one, and some more sections up higher in the profile. And based on an absolute argon age, we now think is more likely that it's actually older than 8 million years. So it's not this option, but it's rather this. But this is an ongoing study, and because this is such a large section, we and there's the biostratigraphy is nice, but it's really not that well defined. We have still problems in getting the absolute age, but based on these preliminary results from Claudia Kuiper from Amsterdam, we think is older than 8 million years. And so then finally, some words about the footprints. So this is Crete here. This is the original paper by Gerlinski, 2017. Here's one of the footprints, and here's one of the tracks, let's say. So I think there's around 50 footprints in this site. This is the site, more or less, a very, very nice beach in northwestern Crete. We went there in out of tourist season, so it was really nice, not too much crowded. And on this surface, they found these footprints, and they made analysis. They made comparison. So this is from the original paper. Comparison with primates and animals like bears, I think. And they also made some like modern day footprints, and they made some kind of cluster analysis. And they claim to me at least, kind of convincing that this is Laetoli track member modern humans and Trachylos. So Trachylos is gray, and this is primates or baboons and other primates in general. And they claim that there is a specific difference, especially with this thumb toe, which is in Trachylos is really not has no angle, but it's really aligned with the other And so they claim that they have this age, which as I said, the problem of these footprints really was that the age is really loosely defined. So we went there again, took samples for magnetostratigraphy. We did, these are the results. They look very nice. Only normal polarity. We did some rock magnetic experiments, some other experiments. We reanalyzed the biostratigraphy, which has some specific foraminifera, and which we used to further refine the age, and then finally came up with the this normal polarity chron, a bit older than 6 million years. We used also some magnetic susceptibility to obtain a cyclostratigraphic picture, but in the end we are fairly sure that we are more or less around 6 million years old for these footprints, and not older and not much younger. So what did we achieve in the end? This is the picture from before, and this is the picture now. So we gave Danuvius a much more precise age, about 11.5, 11.6 million years old, which doesn't change its position very much in this evolution. However, Udabno went down, and this is not really a special Dryopithecine anymore. So it's just one of the latest ones. So this will change the importance of Udabnopithecus very much in this evolution. And we gave the Trachylos footprints a precise age, which is very young compared to the other European hominids. But if it actually is a hominin, so a bipedal upright walking hominid, it would really be the oldest by far, and outside of Africa, which would make this would really change the evolution of hominids as we see it. But of course, these are only footprints. So we need actual findings to prove this. But this again might argue that this connection area of Europe, Eurasia, and Africa might play a more important role than just the Eastern Africa areas or Southern Africa, as other people think. But it makes things more complicated, which is of course, to me, it's a very interesting thing to study. And I mean, a lot of open questions are still there in the research of hominids, which. And so the conclusion is the dating of hominids is still a major task. And so some certain aspects are still extremely difficult to assess. So how did these migration routes, why the hominids became or disappeared from Eurasia again? People argued with some climatic crisis, which it's very intriguing. But we need precise times when they disappeared, and now it doesn't seem to fit very much the Valesian crisis to the disappearance of the hominids. So the multidisciplinary approaches are necessary, like in Trachylos, and magnetostratigraphy is still a very important key tool to add information to this stuff. And I will not talk about this, but one very interesting thing is especially like what we came across in the studying the Trachylos footprints. So we also did, first of all, to get additional constraints for the age, we also did uranium-led dating of the trial zircons, and this is the age spectra. So there's no actually age range, but this is 0. This is 500, 600 million years, and this is probably 3 billion years. So this is all the early Precambrian stuff, and this is really the Pan-African peak. So this led us to believe that this might be related to Aeolian input in the Trachylos site, which is in Crete. So because it's so far away from Northern Africa, our explanation was that it should be Aeolian in origin. And at this time in Chad, so this is from where they found Sahelanthropus, which is a similar age finding from Northern Africa. They also have dune remains, and also Ororin in Kenya also has some red sedimentary layers. So this might indicate because people argued that this is the time when the Sahara Desert appeared for the first time. Other people argue it's much later, but if it's true that this was so early, the evolution of this desert belt, so Sahara, Arabia, Central Asian desert belt, this might really actually be related very much to the hominid evolution as an obstacle, or as some kind of vicariant agent pushing or separating different lineages of hominids. So so this as a climate forcing mechanism might be very important in the human evolution studies. And to correlate this, paleomagnetism can be used because you need this first of all this temporary resolution, but you can also use magnetic proxies to actually identify and quantify the aeolian input, and this might become a interesting research field and add more stuff to that. And the other thing is that, or the next point is that this Sahara Desert evolution has been related to the shrinkage of the paratitis, which so this is a modeling study, modeling different basins and different like ocean currents, and they argue that this could be a mechanism for aridification in Northern Africa. And to really correlate these two events, also magneto and cyclostratigraphy are very important. And then finally, which is related to all of this, the role of seasonality and orbital forcing in this climatic evolutions, and then the impact on the human evolution. All right, thank you very much.
All right, thank you, Uwe, for a great talk. And we have some time for questions, like 5 minutes. I have some questions.
Should I stop sharing my screen, maybe?
Sure. Questions? If you have a question, just unmute yourself and ask away. Okay, I'm going to start because I have. So I was wondering. Well, first of all, you've shown the. Maybe you should. You will have to share your screen again.
Yes.
In the Georgia site, I was wondering if there appears to be some extra or excess reversal there in one of your, which maybe you can show again the record you got. It's really at the very end.
No, Georgia is really a tricky thing.
One more. No.
This one?
Yeah. So the I'm looking at the lower, panels, the Chuna, I think it's called.
Yeah. This one's here.
Yeah, there appears to be several, additional reversals. What's going on there?
Yeah. No, I mean, starting in the Pleistocene, you don't expect. You expect everything to be nice. Like if you have a couple samples with a certain polarity, it has to be there. And if there's nothing there, there's something wrong. In the Miocene, I mean, first of all, people argue that there might be some hidden crons, they keep appearing. Like there's some IODP works and they get some strange polarities, so some small crons, and they say, okay, we have to define new crons. So normally, to make a correlation like this, there has to be some other constraints, and we make this because somewhere here I think we have an absolute age which is now 8.8. Which is like 8.5 million years. So we have to bring this in there, and other people are making. I mean, I have to check this again, but if it's just one or two samples, we can make it gray. I mean, you see that there's really this is not a straightforward thing in the Miocene to do this. The samples are normally not as perfect, so we have extended also this section, so we want to see if these small crons are there in every parallel section. So that this would be an argument to say, okay, something was wrong there. So yeah, I mean, I keep working in this age period is really not that satisfying, because yeah, it's you I mean the Dutch, the Utrecht group, they work a lot a bit older in the Paratitis region, and you look at their correlations and at their pattern, and they are different all the time. And so it's really a thing if the polarity timescale is not perfect, or if this sedimentary signal is also very hard to identify it sometimes, like when there is greigite involved, or the weak signal, very weak signal. So this is also a process. And I would always say that like some of my teachers told me is, we have to present all what we have, and then we come up with a correlation. And then, because the original data, this can really change. And at some point, people can say, okay, this is much older, much younger. I mean, like also Danuvius, I'm not that sure that this is the actual age, because the pattern is so strange. And these two hiatuses are very long. And I would have put it a bit older. But if you make it older, you change the whole story of paleontological evolution in Europe. And this is this is a big thing to do. And you upset many people in Austria and in Switzerland. And so, I mean, I think this is always, especially in this time, where we don't have a lot of absolute age constraints, it's really a long ongoing thing to refine ages. And I would never say that the final correlation is always the end of the story, but the data should be as good as possible.
Can the difference between these absolute or independent age constraints and magnetostratigraphy come from the time it takes to acquire or to record? I mean, you mentioned that in sediments, it's complicated, right? It can take time, to really between the position and when the signal is being recorded. So what you just said made me think that.
I think this is really happening, but not on this time scale. I mean, this lock-in depth. There can be changes in lock-in depths. So sometimes the reverse is happening, and then it switches back to the original polarity and then back. And this sometimes, can be a change in lock-in depth. But normally, if you go to these long time periods and you have an indication of sediment accumulation rate, then it's very unlikely that this is happening like over meters or over 100,000 of years, which is just too long. I mean, this shouldn't. Once it's locked in, that's fine. I mean, you're right, because as I said, it was a bit oversimplified. I mean, what we think now is that, like, bioturbation or like a change in pore spaces, this is really allowing the particles to align with the field, and this makes then the nice recorded field. And so this is not happening when there's everything it can move, but it's happening when it's compacted. This is, I mean, there's these things, but I don't think that this will change a lot. It's maybe normally these sedimentation processes, they are very complicated, but some are like taking the average, it should behave more or less similar. So there shouldn't be, you cannot explain this a whole chron of a couple meters by these kind of processes.
Boaz, you have a question? I see you unmuted yourself. Boaz, is that a question? Nope, that was an accident. I have another question, but I want to give some people an opportunity. Okay, I'm going to ask it. It's a more general one, and it's I was wondering. I mean, you said you're not an anthropologist, but are there ideas out there about how humanoids ended up in Crete, which is an island?
Yeah, I
how
mean,
did they get there?
Yeah, the idea is it was not an island back then. It was connected to the mainland. I mean, there's even some indication about subsidence and these kind of evolutions. So it was a different landscape there.
Okay.
So and it's very close. I mean, it also, there is a rotation going on in Crete. I think it's like, you know, this, it was in the beginning, it was fairly straight, and then the western part of Crete rotated. So it opened up a bit. Yeah. Not much. I mean, in 5 million years, 6 million years, not much happened, but it was some stretching there. But yeah, it's very likely that all this was connected, and it was a shallow. It was similar as it is now, but I mean, we don't have, it's fairly close to the mainland, so we don't have to infer. I mean, like this kind of studies, they propose every sorts of things, like swimming on the elephants. There's great stuff, but we don't need this, I think, to come up with hominids in Crete.
Awesome. Anyone else other than me? Okay, it seems like you're off the hook.
Okay.
So I would like to really thank you again for really a thought-provoking seminar, and we hope to see you here when.
Yes, I will start to make the planning. That would be a great thing to do this early next year. Yeah,
awesome.
Great.
Awesome.